just distributed the assignment sheet, and I have indicated that even though I said yesterday that equations of state are not directly included in the portion, question 3 simply regards, asks you to calculate the departure function for the given equations of state. That you should be able to do. You will in fact take that up in today's class. So the formula have the equation of state as the input, and all you have to do is to carry out the necessary integral. Given any equation of state, you should be able to do that without any problem. The actual details of the equation of state, for instance, finding the parameters in terms of the critical constants, or finding the saturation pressure, and so on, those will not be asked in the quiz. So certainly departure function is very much a part of the quiz. We already have formula for the departure function in terms of the equation of state. So you should be able to calculate them given any equation of state without knowing about how the isotherms look for that equation of state, or how the parameters are to be estimated, and so on. Right? So that is the point I wish to make. We now continue with the equation of state, and we take up those equations of state that are given in the assignment. We solve it for the van der Waals equation of state. We can express A as well as B in terms of any two of the three critical constants, and it's commonly expressed in terms of TC and PC, because they are the more accurately supposedly known. Right? That's the important step that will connect any equation of state to an actual substance, because I can choose any other equation of state also. The question is, how are you going to assign the parameters for a given substance? So first step is to try as much as possible to differentiate as 4 parameters. Then we have only 3 constants. We cannot determine all of them by critical constant. We need some other method to calculate all the parameters. Right? So 2 parameters, certainly 2 critical constants is sufficient. You can choose any 2 of them. Right? And so we got the expressions. I don't want to write them again. But the important property of the van der Waals equation of state is also its limitation is that it predicts a constant critical compressibility. So if you have decided to model a substance using the van der Waals equation of state, then you have no choice over what the critical compressibility of that substance is. Whatever it is, van der Waals says that it has to be 3 by 8, and we saw that the actual is actually 0.375. The actual is much different, and that is why van der Waals is not really known for, even though it gives all the qualitative features of expected of phase behavior, especially liquid vapor transition. It's not used for practical calculations because it's not numerically accurate enough. Okay. So as an attempt to improve the numerical accuracy, we look at many have been proposed. There are still people writing papers on equations of state with 7, 8 parameters and so on. A lot of it is empirically fitted. We'll take up 2 of them. One is the so-called Soave-Redlich-Kwong, named after the 3 persons who proposed it, and the formulas are given in your and the SRK is E equal to RT by P minus P. So that part is the same. Minus A times alpha of T, that is a function of temperature. We'll call it SRK. Divided by, this is now different. So V squared, we have E times B plus B. Now another more famous, more widely used is the Peng-Robinson. And for that, the pressure is of course I am using using B for everywhere, the B corresponds to the Peng-Robinson parameter. They will not be the same. So the A and B that appear here and here are not the same as the A and B that appear there clearly. Both cases, the form of alpha is chosen so that both of them become 1 at the critical temperature, functions of temperature. So that is the third, it's like adding a third parameter which is a function of temperature. It's allowed to vary with temperature. Now you will find that we don't want, I'll get into that later. Now, how are we to find the parameters A and B in terms of TC and PC? You can find, but you will find that this limitation of constant critical compressibility is not overcome by any of these two equations of state. Because at the critical point, alpha will become 1. So we again have the same thing as the van der Waals, two parameters A and B. You can choose any two of the critical constants, right? And you can choose TC and PC, and you will find that both the SRK and the PR equations of state both also will predict the constant critical compressibility, but it will be different from that of the van der Waals. I think it's probably I don't remember the exact numbers, but we can easily prove that you can have it here. Yeah, the SRK has a constant critical compressibility of 1/3, whereas this is certainly they are closer to the actual ones, whereas this is 0.31. Peng-Robinson. So what is the advantage of introducing the third parameter? And this is at least what these people did. So they introduced the third parameter as a function of temperature. They determined this quantity alpha, right, at each temperature by matching the saturation pressure predicted by the equation of state with that of the actual saturation pressure of that substance. So you take a particular substance, let's say methane or ethane, and then you calculate, you know what, let's say you take a temperature T1, right, and then you know what the experimentally formed saturation pressure is. So then you have to do the saturation pressure calculation, which we haven't done so far. And so we try to find what should be this quantity, alpha of T1, so that the Psat predicted by the equation of state is Psat experimental. So within some tolerance limit, won't be exactly limit, you say within 1% or 2% you say. And so you choose, so this alpha, so function of temperature is chosen as a fitting parameter so that the saturation pressure, but of course they didn't choose all possible substances, they probably choose some 15 or 20 substances, and then they found the alpha as a function of temperature for each substance. And interestingly, they found, and you will find here, that the alpha function, and they plotted the alpha versus T, they found for both SRK as well as PR, both of them found a similar temperature dependence of the alpha, so that the temperature dependence can be expressed in terms of a single parameter. It's somewhat long-winded, so you have to follow what I am trying to say. So the first step is how they found the alpha, right? So saturation pressure you calculate from equation state, match it and choose vary the alpha at each temperature, right? So that the predicted saturation pressure matches the experimental one. So then you plot the temperature versus alpha. We have now got it at various temperatures. right, between the triple point and the critical point. So now you plot it, and they found that the plot can be approximately represented by the following functional form. And it has, there's nothing unique about this. They just chose this form and they found that it fitted the temperature dependence of alpha quite well. So I have, in fact, this K should also be SRK because it is different for the two, so that is not really indicated here. Maybe you should just add that. So alpha is 1 plus some other parameter they call as kappa, and 1 minus TR. Now TR is a reduced temperature. So it is defined as T over T. This is how they chose to represent alpha square. Now Peng-Robinson also similar procedure they adopted, but I think Peng-Robinson studied many more substances than the Redlich-Kwong, and so they also got a very similar form. This is the form they roughly fitted. So they said, they found that the dependence of alpha on temperature could be approximately represented just using one parameter. So now this is a new parameter. So now we have, right, what we have done by now fitting it to this form. Now I have 3 parameters in each of the 2 equations of state. So it is obviously can be expected to be superior to the van der Waals because now you are having an additional parameter, namely the. This will vary from substance to substance, right? So you could tabulate the kappa values for each substance, and because the equations of state are different, clearly the same procedure of matching the predicted saturation pressure with the experimental saturation pressure will utilize the different values of kappa for each. For the same substance, you get different kappa values depending on whether you use the Peng-Robinson or the SRK. That's what they found. And further, you will find this other equation, which I am going to write down just for the SRK. So the another plus 1.574 omega. Now this omega is what is called as the eccentric factor, and it's also defined in the assignment sheet. The omega is defined as somewhat very convoluted, and a lot of it, all of it is empty. There is nothing fundamental about any of this. It's just a third parameter which is made to depend on temperature. You are fitting it with the saturation pressure data for some substances, and then you are finding the parameter for each substance. Then they found that it is more convenient rather than listing the kappa for the various substances for each equation state. They found it more convenient to fit it with another parameter which they call the eccentric parameter, which is defined already. It was defined already existing. It was -1 minus logarithm to the base 10 of the saturation pressure of a substance at a TR of 0.7 divided by the critical pressure. Now I think the background to this is you might wonder how anyone can come up with such a convoluted formula, and what does this eccentric factor mean, and what it means roughly is that now if Psat by Pc, Psat at TR equal to 0.7, that's a reduced temperature of 0.7. Okay, so we said that liquid vapor coexistence curve runs all the way from the triple point to the critical point. Right, so 0.7 is actually not, the 0.7 absolute T by Tc, so maybe 0.7 will be somewhere close. So this temperature is T, which is 0.7 times Tc, let's say. So calculate the saturation pressure experimentally, it is available. The experimental data is available. We sat at here to 0.7 by PC. Now, suppose that is equal to 1, or maybe it cannot be 1, when it is 0.1, let's say. It is 0.1, what will happen to this? Suppose, let's say, it is 0.1. Now, logarithm to the base 10 of 0.1 is minus 1. So, minus 1 minus 1, so it becomes 0. So, I think what they found was for a lot of the substances called as spherical in some sense, like inert gases like argon and so on, and spherical molecules like methane and so on. Spherical in some crude approximate molecular sense. They found that this was the saturation pressure at a DR of 0.7 was approximately 10% of the critical pressure. That's what they found. It was found much earlier. And so you define a new quantity called the acentric, and that is, in some sense, defines the degree by which the substance will not be spherical. That is defined by using this formula. So if this becomes 0 for the so-called spherical molecule, for any other substance, for which it will not be 0, it defines a certain degree of asphericity, or it is called as acentricity, or the acentric factor. So what is, because that is the saturation pressure data is available, you can go and find the acentric factor for any substance very easily. Much easier than. So what they did was, rather than listing the copper values for each substance, they just fitted it to the acentric factor. And so you can simply, given any substance, in fact this can now be extended even to substances which they did not study. You sort of extrapolate and say that the same formula can be used, so relating the kappa to the acentric factor, and you can probably use that some degree of reliability. There is a lot of empiricism in this. But what we now look at is, these are the three most commonly studied equations of state. You will see how to calculate the departure function, right? Take one or two of these and then see how it will turn out. Now you can see for the departure function, basically you need to be able to evaluate the following integrals. Call this I1. Integral 1 is integral infinity to V1. So you should know how to do it properly. That's all. It's the only question of integration. Handle the infinity limit carefully. This is the integral. It appears in H as well as in E. Departure function for H and E. I have to calculate other terms such as P1 minus RT1 and RT1 logarithm of P1 V1 by RT1 and so on. That simply has to be added or subtracted. If you want to calculate any departure function, you need to be able to calculate these integrals. The other integral is integral infinity to V1, I2, I4. Temperature is important. So we calculate that the particular temperature T1 minus R over V, dP by dt minus R over V. This I2, this comes to the departure function for S, and then we have another integral that call as I3 V1 infinity to V1 again. RT1 by P minus P of P1 dP. This is coming in the departure functions for A and G. Now the crucial point is that van der Waals will be the simplest. The complication would arise for these two equations of space, particularly for, not so much for this, but for these two, because you have to calculate dP by dt, and you have to be aware that this alpha is actually dependent on temperature. We are differing slightly in the notation, in that some people simply call it A of t, right? So we are not doing it. We are distinguishing the A is constant, and we are putting all the temperature differences in a new function, right? So let's now calculate the integral. The simplest is the van der Waals, for which it will be very easy to calculate these integrals. Now I1 for the van der Waals. Right? So what I need is dP by dt. Now dP by dt for the van der Waals is simply R over V minus P. Right? It is independent of temperature. So that is what further. So I have T1 dP by dt. It's independent of temperature. So function only of volume. Minus P is given by RT1 by V minus P minus, right, P itself. So that also has been evaluated at T1 minus RT1 by V minus P minus A over V square. This will make it very straightforward. So this is simply equal to A over V square. Right? So then I1 can be calculated as integral infinity to D1. Right? This whole thing is just A over V square dV. So this will be minus A over V, the integral. So this is simply equal to minus A over V1. That's all. So I can now very easily write, for instance, I1, I can write for the van der Waals, the formula for E minus EIT is immediately written. It's just this integral, I1. So it is simply equal to minus A, which is in fact independent of temperature for the van der Waals equation of state. It's simply equal to minus A over V1. H. So when we replace this by H, it's all of this, the integral plus T1 V1 minus RT1. That's all. So you know what is very easy to calculate the departure functions. Just involves calculating these integrals, right? So similarly, you can do the other thing, dP by dt minus R over V, right? For S, I get dP by dt minus R over V is what I need, integral infinity to d1 dP. Right? Again, dP by dt is R over V minus P, so that's simply integral infinity to v1 R over V minus P minus R over V dP. So again, you have to be a bit careful, because when you calculate each one of the integrals individually, then you will see that both of them will blow up. And some books introduce some quantity called V infinity and make a mess of the whole thing. But there is nothing like that is needed. This is the whole integral together. You don't need to look at them separately and plan into a curve. Clearly, the integral of R over V minus P minus R over V very simply written as R logarithm of V minus P by V. It's very easy. So you just forget about the limits, calculate the indefinite integral. One is R log P minus P, another is minus R log V. So you combine the two. Now you will see that there will be no problem with the infinity limit. Otherwise you will be run into unnecessary confusion, right? So this is now calculated between infinity and V1. Very easy to see that as V goes to infinity, after all this 1 minus P over V, V goes to infinity, you get logarithm of 1. But you see, this is now the natural log, not the logarithm, the base 10. anyway that is 0. So you simply get R logarithm P1 minus B by P1. Now this integral is automatically equal to S minus SIG of T1 P1. That's again turning out to be independent of temperature. For the van der Waals only this is happening. And for S minus SIG, if you want to calculate Tp, right? So S minus P1 is equal to simply this R log P1 minus, of course that is dependent on temperature, minus RT1 or plus R log P1. So it's quite straightforward. You just have to make sure that you do the integration properly. Now the other one is even simpler. There is not even any derivative needed. You can easily get that other integral. Let's now take up one of these. Let's take the Peng-Robinson equation. Then try to calculate the integral which involves actually dp by dt. This will not cause much problem because the alpha will simply appear there. You still have to evaluate, because if you look at it here, there is no derivative with respect to temperature. But the alpha, which is a function of temperature, has to be evaluated separately at each temperature that is given. That is something that you will have to remember to do. Let's take up the I1 for the Peng-Robinson and see what is involved. The formula would be obviously a bit more complicated. So first it is always better to calculate the integrand first. I'll just take up the SR, because this integration is easier done over volume. Right? So I1 for the SRK. So the complication that comes out of dp by dt will be the same for both the Peng-Robinson and SR. So I1, to calculate that, I need T1 dp by dt of P1 minus P of P evaluated at T1. Okay. So we have chosen, if you look at the books, they probably put all the required functions at some arbitrary T and P or T and B. I have deliberately chosen T1 and T1 because it's convenient then to use the T and P as variables of integration. Otherwise I have to choose something else because I can't fix the value at B and choose that also as a dummy variable of integration. That can lead sometimes to errors. So this is what I need to calculate, and I have to integrate it. So dp by dt, if I calculate for the SRK, is R over B minus P minus A d alpha SRK by dt. Right. Now I have evaluated at T1. Right. So if we want to calculate this as T1, right? So this will be evaluated at T1. First I have to calculate a derivative. That form is given, so we can easily calculate the. You'll see what it looks like. So I leave it as it is here. I won't, introduce additional complications. Maybe this is just a constant. The dp by dt is a function of temperature. But I wanted to evaluate a particular temperature T1 that is given to me. So it's just another constant. You have to evaluate it, that's all. It's not that much more complicated as it might appear. So now let's calculate T1 dp by dt minus P. This is equal to R T1 by T minus B. Right? T1 times this minus A T1 B into B plus B D alpha by P evaluated at T1 is again RT1 by D minus B minus A alpha in this term will cancel, and all I get is this quantity is simply, right, A over B times B plus B. That's really the crucial thing that would have to be integrated, because I'm not going to integrate the function of temperature, whatever it is. It's evaluated at T1, right, times alpha of T1 minus T1 D alpha by dE evaluated at T equal to T1. That's all. So the integration would involve only this, and so if I want to calculate I1 for instance, for the SRK equation of state, integral infinity to D1, T1 A times alpha of T1 minus T1 D alpha times integral infinity to D1 dV by B times B plus B. This can be very easily integrated. In fact, they can probably show that I can express this in terms of some, because the numerical value given in the probably usually calculated to evaluate the integral numerically. If it is not, if I want an expression, then I have to do it. I can look at this like this. Very easily you will split it into partial fractions. So I get B plus B minus B. I get a B in the numerator, so I can easily show that this is 1 over B time. This time very straightforward ways of doing it. You just call it as C1 by B minus C2 by B plus B, and simply equate the two. You can find C1 and C2. Very straightforward way of doing it, right? But you can easily show that in this case C1 and C2 are both equal to 1 over B. You can probably even write that by inspection, right? So this is what I have. So this is all of this factor, which involves A and the factor, all of this to come in times, right? And then I also have B, so I will write it fully. Now for the Peng-Robinson, this factor will be the same, but only this will be for Peng-Robinson. Now that other integral will be different, because that has B squared, plus whatever, right? B into B plus B times B minus B. So that will be a little bit more difficult to split into factors. The same procedure goes. And then I have the integrate, so I will also get a B here, and so this would again be log B by B plus B evaluated between infinity and B1. Again, you can easily verify the infinity limit, the integral would be 0, because I can again write this as 1 over 1 plus B over B, and as B goes to infinity, right, you will get 1 over 1, logarithm of 1 is 0. So we get all of this factor times logarithm of B1 by B1 plus B. That's all. That automatically I1 will give you the internal energy departure function. To to calculate the enthalpy, you just have to add a couple of terms, d1 minus r2. That remains the same. Now the I2, they've already calculated dV by dt, right? The form will be the same for the Peng-Robinson, because the dP by dt and only the volume factor is different for the Peng-Robinson versus the enthalpy. So you can easily calculate, just calculate the integral and that will get you to the rest of the stuff. For this, there is nothing involved at all. So it's easy, no derivative is needed. But that alpha of T1 would come into play because it's part of the equation. So it will depend on the temperature, that's fact. Right? So what I do is just try one or two of these integrals, and the answers have been given references. All the standard references would have the expressions for the departure functions for various some of these common equations, and you can easily verify whether your integration is correct or not. So fairly straightforward exercise. Of course, there should be any other equation of state also. You should be able to calculate the integrals and get the departure functions. Right? Now, what we will do, so are there any questions? So this much what we have covered is you should be prepared to do in the quiz as well, if at all I ask. And there are so many factors that we have covered, right? What if you, maybe before I go to the next topic, we be calculating the saturation pressure. We summarize what we need to know for the quiz, right? And basically, I don't expect you to remember all the, you should know what to remember and what not to remember. So I just want to give you a brief summary. All the definitions you have to remember. You cannot come and say that I need an open book to remember what CB is or how it is defined or how all the quantities that we have defined. Fugacity from you should know how it is defined. Right? You cannot expect to have to open the book every time you are have to. All the definitions you have to remember. These are the basic equations. Certainly, this is the fundamental combination of fundamental and general equation. It's significant you should know. And plus, again, every definition you should know. All you have to do is to know y minus mx versus m. Then you can easily construct even these definitions. Right? It's not coming out of the blue, but based on. Of course, the differentiated dA and all that you can easily derive. It doesn't hurt to remember them. You can easily, with this, you can just take the differential and get it. In case you're confused, so many, some of them have negatives, some of them have positives. You don't know which is negative or which is positive. I sort of remember all of them. But if you're not sure, right, whether it's minus SdV, minus PdV, for example, dE, you can easily out by just remembering these definitions. And the starting, this of course you should remember, the most important. The other stuff from linear transform, if you remember y minus mx and see what m is the slope, here you have two slopes, t and minus p, you can easily get the other definitions. You just calculate the differential, you will get whatever you want, right? So all that you have to remember, basic definition CB, how it is defined, CP, we have seen different ways of defining these, in terms of internal energy or in terms of entropy, you should know how to define them. And also Maxwell's relation, there is absolutely no need to remember, but you're bound to, you can always construct the Maxwell's relations. But two very important, worthwhile, at least this one, I think it's not, doesn't hurt to remember. This is such an important Maxwell relation. You can easily get it once you write all the differential equations. Right? This at least if you remember, the other one is also equally important. At least these two, it doesn't hurt to remember. If you don't want to burden your memory, you don't have to remember. You can easily, you have to remember that two of the Maxwell relations often used. There are two other Maxwell relations. One involves ds by dp and another involves ds by dt. These are very important because they express these derivatives in terms of the equation of state quantities. That's why they are very important. We have used them again and again and again, more than the other two Maxwell's equations. Those I would not even bother to remember. But these are important to realize their practical significance. Right? And then of course we also define beta, and then these quantities we define. You should know what it is. Plus vivacity, of course. I don't know, I might have forgotten some of the definitions. As I said, whatever we have defined as a quantity, depending on its importance, you should remember. Right? Definitely. Now, other than this, the implicit function theorem and the inverse function, you should certainly remember. Right? Basically, f of xy equal to 0. You remember that. And what is y? Let's say e of x or y of x. The conditions of the various formula, and also for z equal to f of xy, the inversion. Those you have to remember. But I have also said by using the differentials, the constructing differentials, you can infer those formulas quite easily. But I would say that you need to remember. It's convenient to remember because we are going to use them again and again and again. And each time you don't want to write Ez equal to something and then do it. Also given quite clearly how the formula come about, right, and how to remember them easily from the single variable case. Right? It's not that difficult, right? And so those things we have to remember. I cannot think of anything else other than some definitions I might have left out. But these are basic things you should know. With this, you should be able to answer any of the questions. Of course, all these departure functions that are given here, I don't expect you to remember at all, but I am sure almost 90% of you will remember all of these and forget this and come. And it will be of no use at all. I remember asking them a simple question which just involves directly constructing a difference between two quantities, and some students had remembered and also wrongly some of these formula. Of course, they don't get any points because you cannot use these without deriving them. You have to use only what is given in the question paper. Right? For instance, if I ask you to derive, it is like saying, if I ask you to derive the departure function for d minus di dt, if you just remember and write the expression, I cannot give you any points for that. You should know what is a derivation and what is simply obtained by just remembering something, right? So I think these important relations you should remember. Other than that, I can't think of anything. If I remember, I will certainly inform you on Monday. Are there any questions about the quiz? Because there's a long break since Monday. Until Monday, and I might be wanting to prepare for the quiz. So I sort of explain briefly what you're expected to know. Because it might be largely analytical and derivation based, but you should also bring your calculator. Right? You give some numerical values and ask you to calculate some of these quantities. Right? So don't forget to bring your calculator. If you have any further questions on the quiz, I can answer them in the Monday class. So other than that, we will begin now looking at the saturation pressure calculation. It's not included in the calculation in the quiz. Certainly is an important topic. We'll take that up on Monday.